by mathematical model, that's a differential equation. Then go to the controllability of the satellite and simulation. Okay, next. We know that mathematical modeling is translating the working of a system, whether it's a satellite system or an electrical system or a human system or a physical system or engineering system. It is we are translating the functioning or working of system in terms of variables, in terms of functions, in terms of equations, in terms of inequations, inequalities. So that's a mathematical model. Next. And various mathematical models are, now we may model in terms of differential equations or difference equation, or can be a stochastic differential equation, can be integral equation, it can be integral differential equation, and various types of mathematical equations can be employed to model a physical or real life problem. Next. So in the present talk, so what I do is we will deal with the modeling using differential equations. Okay, we take up the first one, how to model a physical system or a real life system in terms of differential equation. Next. So if you look into real world problems, whether it's a population growth or epidemic spread or a vibrating system or a heat flow problem, satellite problem or a spacecraft control, climate change problem. So we will first, in the mathematical modeling, we will first identify variables and we will make assumptions, hypotheses, postulations, and we will make use of the laws, maybe laws of physics, laws of biology, laws of engineering, and by using them, we get a mathematical model. Could be a partial differential equation, or it could be an ordinary differential equation, maybe a system of equations. Okay, and we will get an equation of this model. Then, by using the available mathematical methods, we may find an analytical solution, or we may find a numerical solution, or we will make use of some software tools to solve that problem. Once a solution is obtained, then we take the data and validate the solution with respect to the data. If it is not getting validated, we will go back and we will change our assumptions and we modify it, we remodel the system. If it is validated, we will make use of this model for decision making and prediction. Okay, that is mathematical model is what we do with that. Okay, next. And in differential equation, we know that there's a dependent variable. There's a dependent variable and there is independent variables. And the rate of change of variable, the dependent variable with respect to the independent variable is quantified or is measured in terms of derivatives. So thanks to Newton and Leibniz, they introduced the idea of derivatives. Okay, so by using the derivatives, so something is changing with respect to something else. Okay, the temperature is changing with respect to pressure, or pressure is changing with respect to temperature or time. So therefore, the one variable is changing with respect to another variable that is quantified in terms of derivative. So, and the derivative, differential ideas were brought up by these mathematicians, and we make use of that. Next. The development of differential equation is very closely linked with the invention of calculus. Okay, then that happened in 17th century by Newton and Leibniz. Next one. So differential equation provide a mathematical framework for describing dynamics of a system, explaining how quantities evolve and interact over time or space with respect to other variables. Okay, next one. So if there's only one single independent variable, then you say the resulting equation will be a ordinary differential equation. If you have several, then the equation will be PD, partial differential equation. And if you have many dependent variables and one independent variable, then it will result in a system of differential equation. Instead of a single scalar equation, it may result in a system of differential equation. Next. So here we will make use of fundamental physics laws, law of Newton's laws, population dynamics, engineering laws, Kirchhoff's laws, and Hooke's laws, Faraday's laws, and so many laws we make use to get the model. Next one. Okay, the analysis of differential equation provides insight into the system stability, transit, and long-term behavior of the system, especially stability and how it can be controlled, maneuvered. All such things can be studied, and this is used in various engineering fields, and is also part of applied mathematics. Okay, next. So now we will see how an artificial satellite, okay, that is moving around here, that is modeled in terms of differential equation. Next one. So look at, we have Earth, and you have geosynchronized orbit or polar orbits, and we know an artificial satellite is a man-made object that is launched into the orbit, okay, using rockets, and over 12,000 orbits are now there, live orbits are there, including India's Cartosat or ResourceSat or NAVIC, for GPS, and various other application communication satellites, navigation satellites, global positioning, that is GPS satellites, remote sensing satellites. So various satellites are there, and these satellites are moving either in geosynchronized orbits or the polar orbits, and we want to model the movement or the motion of the satellite around the Earth. So for that, see, due to various reasons, various forces, cosmic reasons, the satellites injected into the orbit may slightly drift from the prescribed orbit. So you injected a satellite into an orbit, okay, we assume that we want that it should keep on orbiting in the same orbit in which it is injected, but unfortunately due to some reason it may slightly drift, deviate. While taking photographs, its panels may get disoriented. Instead of taking India's photograph, it may take photograph from Sri Lanka, or it may take photograph from Pakistan, which we don't want. So we want to rectify, we want to bring it back. Okay, we want to correct it. So it may change its desired orientation, either orientation or even the orbit also can be slightly changed. And our idea is we have to bring it back. How do we bring it back? By using some controllers. Next, see how we correct this disturbance or drift. So to correct the deviation, some built-in controllers are already there in the satellite, and they are known as the thrusters. Thrusters are already built in the satellite. So for a satellite, okay, this is a tangential thruster, and this is a radial thruster. So thrusters acting in the tangential direction both back and forth, and thrusters in the radial direction. Here also both back and forth direction thrusters are there. Once we fire these thrusters, it gives a push to the satellite. So this by this motion, we want to bring it back to the normal orbit where we injected. Okay, next. A thruster is a propulsive device. Thruster, what is thruster? Used in spacecraft for station keeping and altitude control. So this is the purpose of a thruster. Okay, it's a built-in mechanism which we do before launching itself. We embed them in the satellite. Okay, now we do a mathematical model. Consider a satellite of mass m orbiting around the Earth under the inverse curve. Okay, next. So the satellite is equipped with two types of thrusters. One is a radial thruster, which I showed, and U2 is a tangential thruster along the direction of the motion. Next one. So this is the thrusters. Okay, in the direction of radial direction, and the tangential direction, you have U1 and U2. Two types of thrusters we next. Okay, if you look into the radial velocity and the tangential velocity, so you can R is in the radial direction, and this is the tangential velocity, and corresponding acceleration component, radial direction, the acceleration, this is a component, and in the direction of the tangential or transverse direction, this is the component of acceleration. Okay, so if then now by applying Newton's law, so mass into acceleration will give you the force. Okay, F is equal to ma. You apply Newton's law, and you get the motion of the satellite. Next one. So this is okay. Mass. We take the mass to be unit satellite mass. It's a m is 1. It's a m r dot, r double dot. It's mass to be acceleration. Is from the previous slide. This is this one. Plus, if you give an external thrust, u1, and here also with the external thrust u2, this is the equation of motion. Where k is the constant k is g into m is a gravitational parameter unit. Okay, and these equations. Okay, this is the force. The inverse square law. Force is coming here. Next one. And if there is no thrust state, u1 is not active, u2 is not active, u1, u2 0, then we know it's a steady state orbit. RT is equal to sigma, which is a constant, means RT is moving around a constant distance from the center, which is circular, and theta t is a movement, angular moment is omega t. Omega is a constant, omega equal to t, and with respect to time, it keeps on moving. So this is an angular moment, this is a radial moment that is constant. Along a fixed orbit, it is moving. This is the motion of the satellite. Okay, and here these constants are square omega square is equal to k, which is required for the circular motion steady state. Now, what we do is we have seen two equations, two nonlinear equations. So we have seen that two nonlinear equations, coupled nonlinear equations, and they are second order. So if you put them into first order equations, so you reduce two second order equations into first order equations, you get four first order equations in terms of four variables. If you take x1 to be r minus sigma, x2 is x dot, x3 is sigma into theta minus omega t, and x4 is sigma into the derivative. Each one, x1 is derivative, x3 is derivative. So if these are the four state variables, state components, then your satellite equation can be rephrased or reduced into a system of four equations. Next. Okay, so this four first order equation, dx1 by dt is x2, dx2 by dt is this linear right hand side. Here the thruster u1 is coming, and the radial thruster, and dx3 by dt is x4, and dx4 by dt is this component which is coming from the previous model. Then u2 is coming here. So this is a complete controlled motion of the satellite. Okay, this is a highly nonlinear system, and the solution of this system is difficult to find. Analytically, it's difficult. For special case, even u1 is 0, u2 is 0. One special solution is the previous one, that is orbital. It is revolving around a circle with a constant angular velocity that we have seen. That is one of the steady states. Otherwise, solution is difficult as the system itself is nonlinear. What we do is we will linearize it. Next one. Next one. Yeah, so in a compact form, the same equation, four equations can be written in a compact form. Dx by dt is equal to f of xu, where x is a vector, state vector is in R4, having four components, and u, the thrust states, is in R2. You have a tangential and radial thrust states, u2, two components. And where this f is a nonlinear function, vector function, and it is defined from the previous four differential equations. Okay, so this is a compact form of writing this into finite dimensional or vector differential equation. Okay, next. As I told, it's not easy to solve this vector differential equation as the nonlinearity is not that very good. So therefore, to tackle, what we will do is we will linearize this nonlinear system about the nominal or equilibrium solution. Equilibrium solution is the circular solution, circular orbit, 0, 0. If you linearize this nonlinear system about this 0, 0, that's initial state is 0 and initial control is also 0, then we get a system of this form. X dot is equal to axt plus b ut, which is a handy equation, a linear control system. Linear control system, and the theory for this system is much rich. We know much things about the controllability, stability, and various fundamental properties of a linear system. So therefore, the nonlinear the satellite problem is reduced into this linear form, then we study it. And then the property will be true only in a neighborhood of the nominal solution, the equilibrium solution about which we realize. So it's not globally. So whatever we deduce for this linear system is applicable only in a small neighborhood, okay, around the 0, 0. Otherwise, it's not true. And usually satellites, when they perturb, it perturbs slightly. No, it's not getting perturbed drastically. So for a small perturbation, this theory is okay, sufficient enough. Okay. Next. Okay, so how do you linearize A and B? This matrix A and B can be obtained. Okay, so if you expand F in Taylor series, okay, vector equation, Taylor series, and if you take the partial derivatives with respect to x and with respect to u, then you get ax plus bu. And explicitly, if you want to see, next one. Yeah. So a is nothing but d, partial derivative of f1 with respect to x1 with respect to x2. So you have these 4 components. Then f2 the same with respect to x1, x2, and if this is the linearization of the nonlinear plan about, and evaluate this one at the pole 0, 0. And so therefore you get the A matrix, the plan matrix as this, where omega is a constant which we define M. Similarly, B is also the same F1 and F2 with respect to U1 and U2. Okay, so with the U1 and U2, you find the partial derivatives, and this matrix is centered. So therefore, the satellite problem, the linearized satellite problem is given by this. Okay, where A and B are. Okay, now I will say something about controllability. So what do you mean by controllability of a system? Forget about satellite. Any general mathematical system, when you say that a system is a control system, and what do you mean by the controllability? Okay, so I will explain it a little bit. So those who are new to the control theory, for them this will be useful. Okay, so being mathematicians, we know that dx by dt square minus 2x is a very simple linear constant coefficient homogeneous differential equation. Okay, and this is the initial condition. Once the initial condition is there, and since this is a linear homogeneous equation, we know the solution ready-made. The solution is e to the power minus 2t, right? E to the power minus 2t is a solution. Since the initial condition is 3, this this becomes your initial condition. So 3 into e to the power minus 2. So this is a solution. If you look at the graph, so you're starting from 3, and there's no there's no control. It keeps on decaying. As t goes to infinity, it dies out. Okay. So for this system, once starting from 3, this is decaying exponentially. Okay, it's dying out as t goes to infinity. So the evolution is not having any control, uncontrolled motion. Now suppose that at say 3 is equal to this, 3 is a time. Starting at t0, that's a 0 time we started. At 3, I want that this system, the position of the solution should be somewhere here. So what do? I want at 3 the position or the state should be somewhere here. I don't have any control. I cannot do anything. But if I add something to this system, it's called a forcing tape. If I add a forcing tape, okay, a non-homogeneous tape, then I may be able to reach somewhere here. Okay. So for example, if I add, okay, next one. For example, if I add sine t, okay, sine t, this is a function, sine t. If I put sine t with the same initial condition, and if you solve it, you see that the system is, or the evolution of the trajectory is going like this. Okay, it's not going to 0, but it is going in this way. So therefore, the trajectory can be controlled, can be changed by adding a non-homogeneous term here, sine t. So instead of sine t, if I put another function, say exponential t, or t square, t cube, then the evolution will be something else. Okay, now controllability problem is, okay, at the time, okay, 10, this time the time is 10. At 10, I want the system to be at 1 or somewhere. can I find a function and I may put that function over here and I find the solution at 10, it will be exactly at 1. So is it possible? That's the question. Okay. And fortunately for this problem, it is possible. Any place you tell me, anywhere you want to keep, okay, when time t is equal to 10 or any time point. So once I start from 3, I can steer it to any place by choosing a proper function here. And how do I make sure that there's a proper function? There's a mathematics behind it. Okay, mathematically we can deduce, find the condition, whether there is a function or not. And if I found that, okay, there is a function, then can you find that function? The answer is yes, you can also find the function. Okay, so that is called the steering function. I am steering the state from any given initial state to a desired final state by using some control function. Then such a system is known as, such a property is known as a controllability. The system is controllable. And this is not only just coming to this system. This is a very simple elementary system, but it comes in real life application anywhere. For example, a satellite problem. Okay, satellite, my panels are like this, and after some time it went to some other orientation. Or orbit is also, I have sigma is orbit, and it went to sigma some value to something else. It is slightly changing. Okay, it's increasing or decreasing. Can you bring it back? So therefore, from a current position, by applying some controller, now this is known this term is known as controller because it can control the trajectory. So this homogeneous term, non-homogeneous term is known as forcing term or a control term by which you can control the evolution of the system. So therefore, such a non-homogeneous term is called a control. So by applying some controller, can you bring it back? Now for students, CGPA, the current semester is 6.5. Now 3 more semesters are there.